All right, let's work through example 4.9. So this is going to talk about yield and selectivity in what's called a dehydrogenation reaction. So first things first, we have two reactions that are happening in this place. They're happening in a continuous reactor at steady state. So first thing that we want to do is we want to say, well, we have reaction 1 and we have reaction 2. And the key thing here that you're going to see me do is that we're going to have one extensive reaction for reaction 1 and one extensive reaction for reaction 2. So this is going to be important because there's different E values, different extensive reaction for each of these two. So it's going to matter whether or not, say, for example, H2 is a product or H2 is a reactant, or something like C2H6 is a reactant. It's also a reactant down here. So that's going to be important because remember, when we do extensive reaction, we have to watch our signs when we're doing certain things. Okay, so that's the first thing to look at. Then let's look at this problem. We have a feed containing 85% by mole ethane, and the balance is inert component. So this is going to happen quite often in problems where the remaining component is inert. So it's just something that's not going to react. That's what inert means. We're going to have a fractional conversion of ethane and a fractional yield of ethylene. And then we want to calculate the molar composition of the product gas and the selectivity of ethylene in methane production, compared to methane production, excuse me. So first thing that we're going to want to do, as always, is figure out what our basis of calculation is. 100 moles in the feed is always a great option if it's not specified for you already. And then what we're going to want to do is we're going to want to set up the problem. So here, let me move my paper down. Here's the setup. We're going to assume that this is stream 1 and this is stream 2. This is some process in the middle that does the hydrogenation reaction. Okay, so N1 is going to be the total mass flow in 1, and that's going to be the 100 moles. That's our moles in our feed. I'm going to say that A is C2H6, B is C2H4, C is H2, D is CH4, and I represents inert. So in this case, we know that 85% of what comes in is C2H6, and the remainder, so 100 minus that, or 1 minus that number, right, is inert component. It's 15%. And then we're going to have some kind of a mass over here in the product, and we're going to have everything in this product because the reactions have gone forward in both these cases. So we're going to have a certain amount of product here. So then the next step to try and get us started is to start to use the extensive reaction to find some molar amounts that are going to be in 2. So we're going to set up a system of equations using this equation. And you'll notice here I've put a plus or minus. Whoops. There we go. I've put a plus or a minus here so that we can really talk about what's going on with this coefficient and this extensive reaction. So let's start by looking at A, our C2H6. Well, we have a certain amount that's going to come out in the product stream, and we have an initial amount. That's not too bad. Now, in both of our reactions, C2H6 is a reactant. So if you go back up here to our equation, reactant in number 1, reactant in number 2. So what that means is we should have a minus sign in front of our V sub I E1 and a minus sign in front of V sub I 2 and E2 in this case. So C2H2 is present in both of those reactions. So we have to have both of those reactions accounted for here. So what that's going to mean is that the 85% that comes in times the 100 moles minus the coefficient in front of C2H2 in the first reaction minus the coefficient in front of C2H6 in the second reaction is going to give us an equation. So now we know that Na2 is going to be equal to 85 moles minus E1 minus E2. So remember, we're setting up a system of equations. So we're not going to do anything with this yet. We're going to wait until we have some numbers to plug things in. So let's do this same process for each of the things that we have. So we have 5 different things. So we need 5 different equations. So just as a reminder, E1 comes from reaction 1 and E2 comes from reaction 2. Let's carry that thought process down as we do the next ones. So let's look at B. B is C2H4. C2H4 only appears as a product in the first reaction, right? So here it is. It's a product in the first reaction. That means that it's a plus when it comes to extensive reaction, and we only have an E1. So you're going to see that we start with NB1, and NB1 is 0, right? We have nothing to start with. And then we add a VI and an E1. So if we simplify this out, we find that NB2 equals E1. Okay, so if we find E1, we know NB2. Let's do C2. Now this one's a little bit complicated because this one's hydrogen. So we're going to have some amount that we start with, which is 0 again, because we don't have anything in the starting component. And then in reaction 1, H2 is a product. So that means we need a plus sign and we need an E1. Now, H2 in the second reaction is a reactant, so we need a negative and we need an E2, right? So let's go back up to the equation so you can see, right? In reaction 1, it's a product. In reaction 2, it's a reactant. So the sign is different and the coefficients are different, and we have two extensive reaction. So what that's going to mean is that NC2 is equal to E1 minus E2 once we solve everything out. All right, let's do D. D is going to be CH4, and it is only a product of the second reaction. We start with nothing in terms of methane. We don't have anything in terms of reaction 1, but we have a 2 as our coefficient, and it's a plus because it's a reactant. So we find that ND2 is equal to 2E2. And then lastly, we have E, which is the inert components, or this should be I. Let's change that up to I. So used to writing E as the fifth letter of the alphabet. We start out with some initial amount, right? It doesn't participate in reaction, so there's going to be no extensive reaction here. So 15% of that 100 mole basis is going to be 15 moles, so we know that we have 15 moles coming out in our reactor. Okay, so that gets us set up to go. Now let's use the other information in the problem to solve for all of these different values. These are what we want. So let's use the fractional conversion of ethane first to help us find Na1 or Na2. Actually, this is Na2 if we think about it, right? So let's put a 2 there. There we go. So we have a fractional conversion of about 50%. So that means that there's a certain amount that happens in the reactor, and this is actually what's going to leave in reactor. So if we convert this amount, right, that's conversion inside the reactor, which means that the remainder is leaving the reactor. So this is 1 minus that fractional conversion. So that's important here. So what we're going to do is we're going to say, well, Na2 has to be the unreacted divided by the fed. That is what yield is, right? This is the definition of yield right here, okay? So if we multiply that by 85 moles, what we're finding is that we should be getting 42.4 moles of C2H6 coming out of the reactor, right? We fed this amount. This is the yield coming out. So if we multiply those two together, we get what comes out of the reactor. So there we go. We've got that value. Now, if we go back to our extensive reaction components and our equations that we wrote, we now know that Na2 equals 42.4 moles, and we know that Na2 also equals 85 minus E1 minus E2. So we can get an equation that says 42.4 equals 85 minus E1 minus E2. Now we can't use that at the moment, but maybe we can use that later on. So we also have information about the ethylene yield to help us simplify further. So ethylene is the C2H4. So what we want to do is we want to think, okay, what would be the maximum yield if everything reacted, right, in the system? So if we feed 85 moles of C2H6, 1 mole of C2H4 is generated for every 1 mole of C2H6 consumed, which means that the maximum yield we would get is 85 moles of C2H4. And if that yield number is 0.471, then the 0.471 times the 85 is going to give us what we actually get out. So remember that yield, this is the denominator of yield, and this is the numerator of yield. Yield is a percent. So what I've done is I've rearranged the yield equation here to say the yield times what we would get if it's in the stoichiometric proportion is what we're actually getting out of the reactor. So that tells us that NB2 is equal to 40 moles of C2H4. Okay, now we also know that NB2 is equal to E1. That's an equation that we wrote on the other side, which means that E1 equals 40 moles. So remember that your extensive reactions have units of moles, and that's important here because that allows us to solve for quite a few things. Now, if we take our 42.4 minus 85 minus E2 minus E, and we put 40 moles in for that E1, then we can find that E2 has to be 2.6 moles. So now we have all of our extensive reactions, which means that we can go ahead and finish solving for NC2 and ND2. So let's do that. So NC2 is E1 minus E2. So we're going to take our 40 and subtract our 2.6 moles, which gives us NC2 equals 37.4 moles of H2. If we go to ND2, that's 2 times the second extent of reaction. So that's 2 times 2.6 moles, which means that ND2 is equal to 5.2 moles of methane. So now we've got all of the N values coming out, so we know the molar composition coming out of the system. The last thing the problem is asking for is to find the selectivity. And it's the selectivity of something relative to something. Remember, it has different units for selectivity. So we wanted to find the selectivity of C2H4 with reference to CH4. So that means we're going to take the moles out of C2H4, which is 40 moles, divided by the moles out of CH4, which is 5.2, and that's going to tell us that the selectivity is 7.7 moles of C2H4 relative to the moles of methane in the system. So selectivity does not have to be a percent. That's an important factor here. Okay? So that problem integrates a lot of different things. It integrates a fractional conversion, and I apologize, this is not yield. This should be fractional conversion. I was getting ahead of myself. That's a definition of fractional conversion. So let's make sure that that's clear in our notes. This uses the definition of yield. And then we also talked about selectivity at the very bottom. So this problem integrates a lot of different concepts. It uses extent of reaction because it's the easiest way to solve this problem, and it uses fractional conversion, yield, and selectivity as a way to walk through this. So take a second and make sure that you understand this process. A lot of these little steps are where you're going to get caught on exams or caught on homework problems. These little steps are really, really critical for these types of problems. So take this time to make sure you have a really clear solution with extra notes in your own notes so that you have it for your next exam.